Okay, so this is the fourth mini course of CTNT 2024 on class field theory by Christelle, Vincent, and there you go.
All right. Yeah, thank you. Okay, this worked out well. Hi, I'm happy to have made it here. As I think Alvaro mentioned, I had a little bit of a health thing last week, and I just wanted to talk about it a little bit. I'm doing well physically. It was like really hard mentally, and I decided to take like a little bit of a time off, like taking the weekend to be with my son and my family. And I wanted to be open about that because I think it's important. Like I feel there's sometimes like a toxic streak in academia that's like, you know, you see these, there was this story recently of like some woman who gave birth and like defended her PhD thesis, like I think like 2 hours afterwards, which is fine, like if that's what you want. And actually, anyway, if you've had a baby, the minutes after the baby's born is the most rested you're gonna be for months, so you might as well just get it over with. But anyway, the point is there's this like kind of toxic thing about like pushing through and like still doing your job and making sure nobody's affected. And I didn't do that, so I hope you still think the class is okay. You know, maybe it's not gonna be as great as if I had spent all last week preparing instead of convalescing, but you'll live, you know? And I think that's important to highlight these examples of times where it's like, you know, being good enough is good enough. And yeah, also, I'm really grateful to Keith and Alvaro for being so supportive and so flexible and, you know, encouraging me to focus on myself. All right. So today, we're going to do many math things. So the organization that I have in mind for us, which is very hopeful, is to start with like a couple preliminary topics, and then talk about class field theory in the specific case of the p-adic numbers, QP. And then once we've kind of talked about that a fair amount, probably today and also tomorrow, talk about abstract class field theory. So class field theory is like a machine, and when you got the ingredients, you just machine the machine and it works. So we'll do it for QP, and then, you know, we'll kind of talk about the machine. And then at the end, I want to do a little bit of Kummer theory, which is like a subset of the machine of class field theory, but can connect back to quadratic reciprocity. All right, so the first preliminary, oh, that's very small. Okay, so the first preliminary is to talk about the ring Z hat. It doesn't really have any other name. Like I looked it up and I was like, certainly it's not just Z hat, but it is kind of just Z hat. Neukirch, that's what I was gonna say. Neukirch, which is the book that I first learned class field theory with, is very soft and smells good. I recommend it. Says that when it first came out, when this ring was new, people called it the proofer ring. But they don't, and I mean, like, I haven't heard it that often anymore, so it's Z hat. Yeah, so that's it, right? You can call it like the profinite completion of the integers. But I was really hoping it had like a better, I don't know. Maybe that's a good name. Maybe I'm judgy. I am judgy. Let's just like put that to bed.
Good judgy.
Well, it depends if you're good or not. Okay, so what is this, right? And I like kind of like struggled with this. So I'm just gonna give you like the technical definition and then tell you what that means. Okay, so technically, it's a projective limit over all integers n of the rings Z mod nz. So the usual integers mod n. Okay, right? So now you can say that to someone and hope that they don't ask any further questions. So what does that mean? So if you have an element, well, okay, so first, sorry. One thing. So what we need, the key point is that if I have two integers m and n, and m divides n, then there is a map, which I'll call phi nm. Sorry, I want to make sure it's like in my notes so I don't mess it up later. From Z mod nz to Z mod mz, which I like to think of as just reduce more. Right, so you have an integer mod n, and then you just think of it mod m instead. And seems innocuous enough, right? But it's important that m divides n so that this is well defined. So that if so I'm thinking reduce more, so kind of like secretly I'm thinking of a as an integer, like not really a class mod n, right? So if I took two different integers that are congruent mod n, right, a and b, they're the same element here, I need to make sure that they go to the same element down here. And that's the case when m divides n. Maybe I'll bring that over. Right, so if I have a congruent to b mod n, that's true if a is b plus some integer times n, right? And so then, because m divides n, I can write also that a is b plus maybe k, l, so here, k is an integer, l is also an integer. So then it tells me that a is also congruent to b mod m. So no matter which representative of a I choose, right, of this class mod n, if I think of it as an integer, and I just reduce that integer more, then I'll get something, and I'll get the same thing as the person next to me who chose a different representative. Right, and you can think of, z mod 6z to z mod 3z. Right, if I choose 1 or 7, they both go to 1 mod 3. Okay, so there's these maps. And I want to talk about z hat. Maybe I can bring the map again one last time. All right, so an element A in z hat is the sequence A2, A3, A4, A5, A6, and so on, forever and ever. An is in z mod nz, and whenever m divides n, then if I take an, I get am. Right, so I have a sequence of numbers. I have a number mod 2, a number mod 3, a number mod 4, a number mod 5, a number mod 6. And what I'm requesting is that whenever there's a way to reduce down, right, so from z mod 6z to z mod 3z, then the two agree. Like, I think of them as like compatible numbers, right? They don't reduce differently. The integers are in Z hat. Okay, but that's a strict containment. There's more, but for example, if I had A, which is like 10 in the integers, right, in Z hat, I would just record 10 mod 2, which is 0, 10 mod 3, which is 1, 10 mod 4, which is 2, 10 mod 5, which is 0, 10 mod 6, which is 4, 10 mod 7, which is 3, 10 mod 8, which is 2, 10 mod 9, which is 1, 10 mod 10, which is 0, and then after that, just like 10, 10, 10, 10, 10 forever, because the numbers are bigger than 10. And here, right, because I started with a number in Z, automatically these are all going to be compatible with each other, right? If I think of 1, 2, 3, 4, 5, 6, 7, well, okay, 6, right? This A6, right? If I reduce more, it's going to agree. You know, if I take 4 and I reduce like mod 2, I get 0. If I take 4 and I reduce mod 3, I get 1, right? Because they both came from like 10 on top in some way. And here I didn't leave myself that much space, right? But eventually it's always 10, 10, 10, 10, 10, 10, 10 forever. And it doesn't have to be that way. You could, you know, keep kind of going up and doing different things there. And so that's why there's a strict containment between them. You could do something more interesting than that, which I think, yeah, I will do in like 2 pages of these notes. To connect to some stuff that you're talking about in other classes, so if you had, right, A2 and A3 already set however you want, we know by Senzi's remainder theorem that Z mod 2Z cross Z mod 3Z is isomorphic to Z mod 6Z, and that in fact, right, if I specify some number mod 2 and some number mod 3, there's a unique number mod 6 that it corresponds to. So, you know, A4, A5, right? My A6 would be set from having A2, A3. My A4 would need to agree with A2, reduce to the same thing mod 2 as what A2 is. Like if A2 is 1, then A4 should be odd, right? But then that's it. I have some freedom to choose A4. A5, 5 is prime. There's nowhere for it to reduce down to, so you're free to choose it as you want. A7, that's a prime. A8, right, should agree with A4, which will agree with A2, so you get a little freedom to choose, but it should still be congruent to A4 mod 4, right? So what I'm trying to say is, where do you have freedom, where don't you have freedom to choose as you're maybe trying to build a number in Z hat? Well, whenever the little n is prime, right, it's the first time that appears, so you can just choose whatever you want. And then after that, when you have a power of that prime, you just need to keep track, right? Like make sure that your A4 will agree with A2, A8 will agree with A4, and so on. My next one here is A9. That should agree with A3. Right? And then I get to A10. That needs to agree with A2 and A5 because Z mod 10Z is isomorphic to Z mod 2Z cross Z mod 5Z. So that one is already decided for me, right? Like I make no choice, right? So for 2, 3, 5, 7, I make any choice I want. For 4, 8, 9, that's a power of a prime. I go look at the previous power of that prime and make sure that that agrees, and then I have a little freedom to choose, you know, like an extra p-adic digit. And then for every other number, right, that's not a power of a prime, I've already decided what it needs to be to agree by Sunzi's remainder theorem. And so one way to think about Z hat, which is different than this projective limit, is that it's the product over all primes of the p-adic integers, right? When you choose A2, A4, A8, A16, A32, you're choosing a 2-adic integer to fill out these powers of 2. When you're choosing A3, A9, A27, as you're going up and they all agree, you're actually choosing like one 3-adic integer, and then a 5-adic integer, a 7-adic integer, and so on and so forth. And then everything that's not a power of a prime is determined by looking at how it factors. Yeah? Yeah? I think we're also going to post it. I mean, like, I'm happy to do that as well, but like, if you miss something and you're too shy to ask, these are going to be online, so don't kick yourself. You can get it later. Okay. So I'm just going to tell you 2 facts, which we may or may not use, but there's a topology on Z hat, which I will not tell you about right now, but Z is dense in Z hat. Okay, so there's a profinite topology that comes from the projective limit, and the ideals n Z hat for n an integer are exactly the open subsets of Z hat. Okay. So that's the proofer ring. Let's bring it back as a word, as a thing we call this. Now the reason why I told you about, I mean, we'll use Z hat, but also now I want to tell you about preliminary 2. Infinite Galois theory. Or just Galois theory. If you're just doing Galois theory for the first time, don't worry too much about the infinite. So you might have seen the definition of a Galois extension. I will give you a definition that works for finite and infinite degree. So suppose that L over K is a field extension. I just mean that both L and K are fields, and K is inside of L. And I'm not saying that L is finite dimensional as a K vector space, not necessarily here. This extension is Galois if it is, first, algebraic, which means that every alpha in L is the root of a polynomial. In kx, right? So some polynomial with coefficients in the base field. When this happens, if alpha is the root of some polynomial in kx, because kx is a PID, then there's a minimal degree that all the, you look at all the polynomials that alpha is a root of, put them all together, there's a smallest degree, and then every polynomial of that degree, you can call it the minimal polynomial of alpha, or you can say that only the one with leading coefficient 1 is the minimal polynomial of alpha, depending on how you feel about things. Okay, but this implies that alpha is a root of an irreducible polynomial. M alpha k in kx, right? So M for minimal, alpha, that's the element, k is the field telling you where the coefficients are. Right, so if L over k is finite, is a finite degree extension, then this always happens. So you know, when you did Galois theory, maybe you did it only in the finite case, so this wasn't a condition. So here, L over k overall might not be a finite extension, but definitely every element in L like kind of belongs to a finite extension, right? So like as a whole, it might be really big, but kind of like when you look closely, it looks a little bit just like a finite extension. Normal, right? So the extension needs to also be normal. So if f of x with coefficients in k is irreducible, and it has a root in L, then all its roots, well, that's very unfortunate. I'm always so hopeful that I will fit the whole thing down there, and I never do. All right, so if you have an irreducible polynomial with coefficients in k and it has a root in L, then all its roots, maybe now I have space, so then all the roots of f are also in L. So I'm not saying that every irreducible polynomial has a root in L. It's allowed to have no root in L, like to still be irreducible, or, well, not necessarily, but anyway, it can factor, right? But if it has one root in L, then all of them have to be there. And finally, separable. The minimal polynomial of every alpha in L over k, right? So this like M alpha k polynomial has all distinct roots. Okay, so this is a little bit of a different flavor of things. Every element in L has some minimal polynomial, and I'm just saying that all the roots of that minimal polynomial are different. There's no repeated roots. And I mean, that non-separability only happens in positive characteristics, so if you've not thought about this a lot, you might wonder, like, how is that even possible? But anyway, when you get in the weeds, it does happen, unfortunately. So when that happens, right, when every element's algebraic, all the irreducible polynomials, when they have, so every minimal polynomial has all their roots in the field, and all the minimal polynomials are separable, it's a Galois extension. And there's a fundamental, oh, sorry. See, I forgot to write it in my notes, and then I added it in, and then I almost forgot to tell you, but I didn't. In this case, if we take the set of field automorphisms of L that fix K, so these are automorphisms, it's not how you spell that, automorphisms of L that fix K, and here I mean like, no, I don't want to use that. Let's call it beta. Right, not like fix K as a set, like sends K to itself, but like fix K, like each element of K stays where they are. We call that the Galois group of L over K. All right. So this is fun. Why do we do that? Because there's a fundamental theorem. So when the extension L over K is a finite degree, a finite extension, then there is a bijection between the subfields that are contained between K and L and the subgroups that are contained between the subgroups of the Galois group. I was going to say between the Galois group and one, but that's just what we call a subgroup of Gal L over K. And the bijection is given by if you have some subgroup, some subfield E, the subgroup H is the Galois group of L over E. So it's a theorem that if L over K is Galois, then L over E is also Galois. It has its own automorphism group. That's a subgroup of the Galois group of L over K. And in the other direction, if you have a subgroup H, then E is the fixed field of H in L, which is the elements of L that are fixed by every element in H. So that's the fundamental theorem of Galois theory. Now, in general, if the extension is not finite, right, so if you remove the hypothesis, this is almost true. You just have to say closed subgroups on that side. So if you've never thought of infinite Galois theory, it's basically Galois theory, except like you worry about topology a little bit on the side for fun. So the infinite extension that we want to talk about in class field theory, this happens. Okay. When I copy and paste and I'm not careful, then forever when I ask for a new page, it shows me that thing again. It's a bug with the program. I teach always, like, you know, with my iPad, and my students get like really used to it, and then I complain about it. Anyway, I will try to be better. Of interest to us, so we'll think of some base field little k. And we'll think of K bar, its separable closure, which is K, right, the base field, plus every element that's a root of a separable polynomial over K. So I don't want anything inseparable, right? Like, it's just, we're not going to talk about that. We're setting that aside, right? So we're just like, everything that is a root of a polynomial with coefficients in K, little k, and that the minimal polynomial is separable. We don't want to deal with distinct, same roots for an irreducible polynomial, repeated roots in an irreducible polynomial. Then the Galois group of this extension is the inverse limit over all the extensions big K over little k that are finite and Galois of the Galois group of K over little k. So what I want to do is to talk about this a fair amount, right? So if I have an element, little alpha, in my separable closure, it's algebraic, right? Because I said I want its minimal polynomial to be separable. So alpha needs to have a minimal polynomial, right? Alpha in K bar is algebraic over little k with separable minimal polynomial over k. And so I can think of the splitting field of that polynomial, right? Because I want everything to be Galois, so I'm going to take little k, I'm going to put in alpha, and then every other root of the minimal polynomial. And that gives me a finite Galois extension, like you might remember if you've taken finite Galois theory. And what I'm saying is that, like, this separable closure, right, it's built out of these extensions. Like, every little element, alpha and K bar, actually belongs, right, to some finite Galois extension, you know, with itself and its Galois conjugates, and they're all together, and that makes me a little finite field extension. And so what I'm thinking, right, this limit, let's bring it over. Okay, let's see. Oh, it's not here. Okay, yes. All right, so I have my little k down here, and then I have, you know, k sub alpha, the splitting field of m alpha little k. All right, that's some Galois extension. I got little Galois elements that are Galoising. And then maybe I have some k beta, right, the splitting field of m beta little k. Those are Galoising on their side. But what I want is to think of some bigger extension that they all belong to, and what would an automorphism here be, right? Well, I can think of restricting the automorphism down to each field and get an element of the Galois group. But I can also think, right, and that's kind of what I did here, right? I had like 10, an element of like Z, a big ring, and then I restricted mod 2, mod 3, mod 4, mod 5, mod 6. And they all agree because they came from somewhere, right? They came from 10. Right? Or I can think of building the Galois group of the big extension by choosing automorphisms at each finite level and just making sure that they agree with each other if I restrict. Right? So that's why I spent some time talking about Z hat, because it's the same idea here. With Z hat, I had a bunch of ZNs. Oh, the Canadian came out of me. I had a bunch of Z mod NZs, right? And I just was careful to pick my little ANs so they would agree and I could build something. You can do the same thing here. Think of each finite extension and pick a little automorphism. And then when you go to a bigger extension that contains it, you just make sure that the restriction agrees. And then that gives you like a bigger automorphism. So you can build kind of from the bottom, right? And this limit here is like under field inclusion, right? Like when there's a bigger one, you know, you make sure that they agree with each other. So that's as much infinite Galois theory as we'll do. It's basically finite Galois theory, but you pick a bunch of it and you make sure they all agree with each other. Kind of how Z hat, you build it out of the Z mod NZs. Yeah. So I'm not going to do that much about it, but that's like something we can do tonight in the problem session. So to define a projective or inverse limit, you need these compatibility maps. So in the Galois case, that would be if I have, like, let's do Q as our base field, right? If you have L over Q, I'll just write right on it, right? You can restrict, and K is inside of L, you can restrict to an element of the Galois group of K over Q. Right, so you have these like compatibility maps. And then, so that was just like talking about the compatibility maps, right? Then an element of the projective limit would be a Galois element for every finite extension, but such that, right, so it would be like A, K, and then there would be like an AL there, right? Whenever K is inside of L, if I take this Galois element, maybe I should call them sigma, that would be a little bit more evocative. All right, then this sigma L restricts to that sigma K. Sorry? Yes. Right, so you're kind of just building, like I think of it as build, like you start, you know, with the automorphisms that sends I to minus I. And then when you go to a field that contains I, that automorphism still has to send I to minus I, but it does whatever else on whatever other elements in there. And then when you go to a bigger field, it still has to do all that, but like there's more stuff and it does something there, right? So you kind of like build it and you just try to make sure that it's compatible so that if you start, you know, if L1 and L2 both contain K, that like they restrict to the same thing so that you actually have like an automorphism, right? You're not just like saying automorphisms, you know, for fun. I mean, you could do that, but it's very, you know. So like that's the vibe that we want to get, right? And if you have an actual automorphism of like some finite extension, right? Like you can just think, you know, this automorphism in every field that it restricts to, and then on the other ones it does nothing, right? Oh, that was that page. And see, that happened again. And let's do an example, an important example. The base field is Fp for P a prime. Okay, so the finite field with P elements. Okay, and we want to think about the Galois group of, well, the separable closure of Fp. Every finite extension of Fp is separable, so that's the same as the algebraic closure of Fp in this case. All right, so the algebraic closure of Fp is made out of smaller extensions, right? You got your Fp at the bottom, and then you have Fp squared, the field with P squared elements, Fp cubed, the field with P cubed elements. These are both contained in Fp to the 6, the field with P to the 6 elements, right? Over here off to the side, Fp to the 5, Fp to the 4, and so on, right? Like that's a fact that Fp to the R is contained in Fp to the S if and only if R divides S, which is what I was trying to draw here. And we know, or I'm telling you if not, that the Galois group of Fp to the n over Fp is cyclic of order n. And it's generated by the element which sends x to x to the p. Okay, so z mod nz is generated by 1 plus 1, right? So the notation's additive here. And the Galois group of Fp to the n over Fp is generated by raising to the p. So the automorphisms are raising to the p, raising to the p squared, raising to the p cubed, and so on, up to raising to the p to the n, which is the identity on Fp to the n. And so, I mean, if we just write things, right? So this is the limit, k over Fp, finite. They're all Galois, so, right, gal k over Fp. But that's, forgot my arrow, right? All those finite extensions of Fp are Fp to the n. And all of these are z mod nz's. And so that's z hat. There. And there's a 1 in z hat, the one that's like 1, 1, 1, 1, 1, 1, 1, right? 1 mod 2, 1 mod 3, 1 mod 4, 1 mod 5, 1 mod 6. That's a compatible sequence. They're all congruent to 1, mod whatever you want, right? And back up there, maybe I'll write it in blue. It corresponds to sending x to x to the p. It's like the kind of like most basic automorphism of any finite extension of Fp. You raise to the p, and it kind of governs everything, right? When you take this phi and you restrict it here to some extension, you know, of degree 3, then now this phi has order 3, right? Because when you raise it to the 3, it's the identity. So you have this map phi on this big extension, right? Like I wish I could draw. Wish I hadn't put myself in a little corner there, right? So there's like a phi, and it restricts to every finite extension and generates the Galois group of every finite extension. And in a sense, right, not in a sense, topologically it generates like this whole Galois group of like every extension of FP, every finite extension of FP. Yep.
So is the Galois group of like FP bar of FP, is that the same as saying all the automorphisms of FP bar that fix FP?
Yes.
Okay. So it's not just that the automorphism group is contained in this in the same way that Z is contained.
Yeah. Yeah. And I'm going to go for it in 2 minutes. I can try to exhibit an element of this Galois group that's not like just a straight like integer power of it. Okay, and we'll do that later. Okay, so there's this phi, right, which sends x to x to the p, and I want to exhibit some psi that's not a power of phi, right? That's not like x to the p to the n for some n, which is the same thing as trying to exhibit a number in z hat that's not in z. So here's one way to do this. For each n positive integer, we'll write n is n prime times p to the e, and the GCD of p and n prime is 1, right? So you like take out the powers of p and you're left with something which we'll call n prime. And you define xn to be the inverse, the multiplicative inverse of n prime mod p to the e. So because n prime is relatively prime to p, it's also relatively prime to p to the e, so it's a unit mod p to the e, and you can find some number xn such that xn times n prime is 1 mod p to the e. And then you define an to be n prime times xn. And you let your phi, right, which is in this Galois group, so it's going to be, whatever it is on FP squared, right? You restrict it. I'm really thinking of building an element of this big Galois group as like telling you what it is on each finite extension, right? Like that's how I can tell you how things act, right? So I think like what does it do on FP squared? What does it do on FP cubed? What does it do on FP to the 4th, and so on, right? And you put psi n to be that Frobenius to the an for this an. And now I'm 1 minute over, so homework, right? I guess we can prove tonight that this is well defined, that if m divides n, then an is am mod m, and so that the restriction of psi n to the field with p to the m elements agrees with the psi m that I defined in there. And so this gives you like a family, like an accumulation of size at each finite level, right? That together gives you an automorphism on the algebraic closure, but that's not like just a straight, raising to the p to the l or p to the whatever you want for any integer. All right, so next time we're going to talk about a little bit more this element, the Frobenius, and how actually every finite field has a Frobenius, and then we'll be able to launch into class field theory for QP. So that's it. I don't have a goodbye slide.